In this video, I will implement Wgan or Wasserstein GAN from scratch with PyTorch. And as a prerequisite to this video, I did another one just yesterday, which was about understanding the architecture of Wgan. So if you are not too aware of the architecture of Wgan, do watch that one first. Otherwise, let's start. Another quick point that in this video I have implemented a very simplified version of Wgan. So to keep it simple, I have kept one slightly advanced topic within Wgan called gradient penalty out of this. But I will do another video after this which will include gradient penalty implementation as well. But that's in the next one. So stay tuned. Hello, my name is Rohan-Paul and very welcome to my computer vision and deep learning YouTube channel. Let's get started. One more thing, that over the next month, I will do many GAN or generative adversarial network implementation from scratch with PyTorch. So do subscribe, because you hitting the subscribe button is what keeps me motivated to do this. Let's start. First, a quick recap on Wgan. So let's see what is the difference between a Wgan and a normal regular GAN. So here in this slide, we can see a regular GAN on the top left corner image and the Wgan architecture on the right bottom corner. So some of the differences with a regular GAN is that in discriminator of a regular GAN, it takes real samples and also images, that is samples generated by the generator architecture, and then the discriminator discriminates between them, that is it produces a binary output of 0 1, that is real or fake. But in Wgan, the discriminator is called critic, and that's because it really does not produce a binary classification kind of output. Rather, it produces a score, a critic score. So it takes both real images and fake images, and then it produces just a single score, which is high for real images and low for the fake images. So in Wgan, the critic is actually a regression problem because it produces a score. And then the next important point to know about Wgan is the concept of Wasserstein distance. So basically, in a Wgan architecture scenario, we have two distribution. One distribution is coming from the real images. This is denoted by P data or PR, and then we have a second distribution denoted by PG, which is the distribution that comes from the images generated by the generator. So we can see these two probability distribution are far apart, and the whole purpose of Wgan is to bring these distribution as close as possible. So it's just this, to bring them closer, and to bring them closer, that is two distribution to be as close as possible, we have to calculate the distance between these two distribution, and that distance calculation is based on Wasserstein distance in Wgan, and that's why it's called Wasserstein GAN. And then overall, these are some important points to note comparing Wgan with a regular GAN. The first one is, after every gradient update on the critic function, we need to clamp the weights to a small fixed range, and the range will be defined as a hyperparameter, and normally it is denoted by between -c and c. So we have discussed this point in detail in the previous architecture understanding video, that the weight clamping or weight clipping is required to maintain the one Lipschitz continuity, and what that means in the context of Wgan. Then the next point is, use a new loss function derived from the Wasserstein distance. No logarithms anymore. The discriminator model does not play as a direct critic, but a helper for estimating the Wasserstein metric between real and generated data distribution. And empirically, the authors recommended in Wgan RMS prop optimizer on the critic rather than a momentum based optimizer such as Atom, which is normally used in other regular GAN like DC GAN. So the main 3 points in Wgan is critic weights clipping, then update critic more than generator, and use RMS prop stochastic gradient descent. So putting it all together, this is the workflow of Wgan. First, the critic network is trained on a real batch of data, then trained on a batch of data generated by the generator. Then the critic's loss function is arranged such that it estimates the Wasserstein distance. That is, it maximizes the distance between the two distribution, and the two distribution is one coming from the real images and one from the fake images. Then the clips the critic's own weight to ensure it is one Lipschitz continuous. and then the generator generates a new batch of images from the noise vector, passes those images through to the critic, and the critic informs the generator of the Wasserstein 1 distance between the true distribution and the distribution of the images that the generator just created. Then the fourth step is so it does these via the loss function of the critic. The critic's weights are frozen and the error propagates all the way back through to the generator, who then updates its parameters to minimize the Wasserstein distance. And these whole steps are repeated until the loss converges to near zero and the distributions are approximately equal. And now I'm back in my VS Code, where the full implementation code is there for Wgan. And just to mention the overall structure of this project, I will have three files. One is wgan.py, which will have the generator and the discriminator, that is a critic code. And overall I have used a very simple linear layer. I have not used conf2d layer here to build the Wgan. And also to note again that in this architecture that I am building in this video, I will not include gradient penalty, because here the purpose is to build an absolutely simplified Wgan. And in the next video I will have another implementation where my structure, the architecture will include conf2d layers and also gradient penalty. So anyway, that's my wgan.py. Then I will have utils.py file. That's a very small file just to include a couple of utility methods. And finally I have a train.py file which will have the whole training flow codes here. And finally, to run this entire Wgan, I will run this on MNIST dataset, and for that I will have another Jupyter notebook where I will just run this train.py file. That is running this entire architecture or the entire project is as simple as just running a single command of Python and then train.py, that is executing the train.py file. All right, now starts with wgan.py. And just like all GANs, the first class that I have within wgan.py is my generator class. And here I have a very simplified implementation of generator class. The first method within generator is this block method, and this just implements one linear layer, then a batch norm 1D based on a condition, and finally just appends a leaky ReLU to my layers and finally return that layer. So I have and the application of this batch norm 2D is based on this normalize argument that will come as an argument to the method. And this condition is because the first layer, when I will implement this block, the very first layer will have the normalize set to false, because that will not have a batch norm 1D, and rest of the layers will have the batch norm 1D applicable. So and then in my next section here, I'm just applying or invoking this block method 4 times. So I have a nn.sequential defined here. The first one is block. In features will just be as usual the latent dimension, which is my noise vector. That is the very start of my generator network, because the whole generator network's purpose is to take in this noise vector and finally output a image from its output layer. So that's why the in features here I'm passing the latent dim, out features I'm keeping at 128, and because this is the first application of the block, I'm setting normalize equal to false. In this case, this batch norm 2D will not be appended to my layer. And then I'm invoking 3 more blocks, and each time only difference is that the out features from the previous block becomes my in features from the next block, and then the out features of this block is something that I am defining separately. So and obviously because these block will also have these apart from the linear layer, it will all these individual blocks will have batch norm 2D and leaky ReLU appended to it. And then the forward method in my generator class just executes or invokes these sequential model that I have defined here. So the forward method takes as its argument the image shape and the z noise vector, and passes that z through my model, which will produce an image, and then it just applies view to flatten it and returns that image. So basically, my whole generator model takes as input a point in the latent space and outputs a single 28 by 28 grayscale image. Remember, in this case, I'm applying this whole Wgan generator and the critic network on MNIST dataset. So it has to produce, the generator has to produce an image which resembles a single image of MNIST dataset, and that's a 28 by 28 grayscale image, and that's why the output from generator here is also a 28 by 28. And this whole generation process is achieved by using a fully connected layer. In this case, I'm using linear layer, which is a fully connected layer, to interpret each point in the latent space. This is then upsampled through these sequential models, doubling the size each time. So that's my generator, and the next one is the discriminator, or as it's called in Wgan, the critic class. So here is my critic class, a very simple implementation of that. And remember, the last layer of generator was to produce this linear layer where the out features were this value integer of np.prod image shape. So that should be my in features at the very first layer in my critic class. So that's why we see the exact same thing in the in features of the first linear layer. So here basically I am taking this number, and ultimately at the end of all the layers in the discriminator I am producing a score, because as we know in Wgan there is no sigmoid at the very last layer, because here we are not producing a 0, 1 or true fake kind of binary output. Rather, we are producing a score, a scalar score. So that's what these layers are doing in my critic class. The first one is linear, then a leaky ReLU with 0.2 and in place true as well. Then again the next linear layer, and here the in features is this 512 number is coming from here. Here the out feature was 512, so that will become my in features in my next linear layer. And keeping the out features equal to 256 here. If you look at the structure, compare the structure between generator and discriminator, here I was upsampling, that is out features 128, 256, 512, 1024, and in the discriminator or the critic I am doing the opposite, going in the opposite direction. So out features 512, then next one out features 256, and finally my out features is 1, because that's the last layer of my critic, and that should produce a single scalar score from its output layer. Alright, and that's the forward function from in my critic. And basically what the forward function doing is it's just implementing these models. So basically here the forward method takes an image and produce a single score, the single scalar score. So it takes the image as an input to my forward or argument, and then flatten the image, and then the final validity score. To produce the final validity score I just have to pass this image to this model, and that's what I'm doing in this line, self.model, and that takes the image underscore flat as the input or the argument, and this validity score is the final output from my critic. So with that I'm done with this file. Now I should be able to train, but before going to train.py, just quickly look at the utils.py file. There I just have two methods, and they are actually just utility methods, so no complexity, so nothing too much to learn here. It's just the first method, wait init normal. So this method will just create the initialize the weights to the network based on whether it's a conv layer or batch norm 2D, etc. And so when I'm using torch.nn.init.normal, this takes the weight data as a tensor, and then it takes a standard deviation and mean as two more arguments. And to image is just again a very simple method, just to clamp my the input between 0 and 1, And this method for visualizing it just takes an image and passes that image tensor to the CPU, then use the make grid function to create a grid from the images, and then finally just use plt.imshow to actually plot or show the image in my notebook. So finally, here I am in my third file, which is train.py. And remember, these these two files are pretty much independent files, standalone files, but train.py has dependencies on these two files, other two files, because it has to import all these classes to my train.py file, and that's why I'm doing this line from utils import star and the same from Wgan. And yeah, so in my train file, first I'm defining these hyperparameters class, and then actually initiating the values of each of the hyperparameters, like number of epoch, batch size, learning rate, number of CPU, latent dim is 100. This is a noise vector to start my entire generator network. Image size 32. Let's see where I'm using 32 here. We'll come to that in a second. And also I'm defining two variables here, CUDA and tensor. They are pretty much obvious and standard code. So this will be true if my GPU is compatible with PyTorch, else it will be false. And if the GPU is available, then all my tensors will need to use the GPU, and that's what the second line is doing. That is, this tensor will be using torch.cuda.float tensor if the CUDA is true, else torch.float tensor. Only difference between this and this is that torch.cuda.float tensor will be computed with help of the GPU power, else only torch.float tensor will be occupying the CPU, and hence the computation will be on the CPU power only. So I mean, most probably for most of PyTorch computer vision projects, you will be using GPU, else it will be super slow. So this line is kind of important. All right, now coming back to the next section. Okay, so this method, this is again a standard code that you will see. That is, here I'm just data loading, implementing the data loader method of PyTorch to load my data and also do some basic transform on the data. So this here I'm using torchvisions.dataset.fashionmnist. This is 28 by 28 grayscale training images, and download equal to true means that it will download this dataset from Torch Visions if that is not already downloaded, or if it is already downloaded, then it will not download. So that's the significance of this parameter. Download equal to true, train equal to true will just pull the training data and not the test data set. And also I'm applying some basic transforms here, that is resizing my images to image size. And here, remember, this is part of the hyperparameter, and I have defined it to be 32 here. And then standard code, I'm converting them to PyTorch's 2 tensor, and also normalizing using mean and standard deviation of 0.5 and 0.5 respectively. And batch size is coming from my hyperparameter, and I have kept it at 64, shuffle equal to true. All right. And then before starting my train method, I'm just creating the generator and the critic object from the generator and critic class respectively. And to the generator, I'm passing the image shape, and also image shape is actually a 3-dimensional tensor because in PyTorch the dimensions of image are set like channels first, then height, and then width, and that's what this image shape represent. And the second argument to the generator class is latent dim, which is a 100-dimensional 100-element noise vector. All right, and the critic also takes the image shape to create the object. And then my 2 optimizers, just following the advice from the paper, I am using RMS prop to create my 2 optimizers. And to that RMS prop, I'm passing generator.parameters and critic.parameters, and learning rate is coming from the hyperparameter. And then generator.apply weight init normal. We defined this method in our utils file. So that's what I'm applying here to initialize my weights. And then my train method. So here the regular structure. So I'm first looping. There will be two loops. The first one, outer loop, is for each epoch, and the number of epochs is a hyperparameter. And then in the inner loop will enumerate through my train data loader. We already have defined it above here. So that's my train data loader, and that's what I'm looping through inside my train method. And the very first step is to create two vectors, which will, one of these will represent the valid targets, which will be all filled with ones. And that's what I'm doing here, using variable module of torch, then creating the tensor, passing that images.shape 0, because my valid target number of targets should match with the original dataset's number of samples, then filling them all up with 1.0. It's a float value, and that's what I'm using, this format 1.0. And then because these are just target values, I do not need this tensor to have the gradients. So and that's what I'm saying, I'm setting requires grad to false, and doing the exact same thing for fake variable as well. But here only difference is all the values will be filled up with 0.0 because they all represent my fake images. And then these are my real images, which is coming directly from the images. And what is these IMGs? This is what I get while enumerating over my train data loaders, because that will return a tuple of the index number and also the images. And only thing that I'm doing here is I'm converting them appropriately with my tensor variable, because this tensor has been defined earlier to use the GPU to make the calculation faster. And the first then my actual training starts from here. And as the very first step, I'm obviously making use of the 0 grad, and that's because PyTorch stores gradients in a mutable data structure, so we need to set it to a clean state before we use it. Otherwise it will have old gradient information from the previous iteration. And then in this line I'm just creating or initiating my noise vector, and I'm making use of this numpy random.normal method, which will draw random samples from a normal or Gaussian distribution. And the first parameter is mean, second parameter is standard deviation, and the third parameter is the shape of output, that is output shape. And here in this case, the image.shape will be the number of samples, and image.latent dim, it is the noise vector number of elements, and in this case this is 100. And so that's my noise vector, and given, so my noise vector is ready. So now that means if I pass this noise vector as an input to my generator, that will produce my fake images. So that's what this line is about. That is, to my generator object, I'm just passing my image shape that we have defined earlier and this noise vector z. And the output of this is my fake images from the generator model. And now that I have the fake images generated from the generator model, the all important step now, which is to pass my fake images through the discriminator, that is a critic here, and get my loss score from the critic. Now the first thing to understand here is that in Wgan the critic loss is the difference, the Wasserstein distance between two distributions, and very much it's something like this, that is dx minus d of gz. What that means is this dx will produce the this x here, the actual real images. So dx means that I'm passing the actual images to the critic to produce a score. And then in this, the next part of this critic loss, this is the critic applied on the fake images. So g of z, this part that is the inside of this function, this will produce the fake images, and then those fake images will be passed as an input to the critic or the discriminator, and that will be my, so the difference between these two terms is my critic loss. And as per the original paper, and the very fundamental building block of Wgan is that these expression need to be maximized by the discriminator or the critic. And now here in my train method, I'm doing a gradient descent. So my optimizing, I'm actually running a minimization algorithm. So how do I maximize this mathematical expression? Well, you can maximize the mathematical expression by minimizing the negative of this expression, and that's why in this line here I am taking the negative of this. So this will become positive and this will become negative. That is very much what I'm doing, is minus dx minus d of gz. And because these two are minus here, actually this will become the next, this expression will become just a plus. Take out this symbol. Yeah, so this is what I'm doing in this line. So minus torch dot mean critic of real images plus torch dot mean critic of fake images. And now my d loss is calculated, so I am ready to do the back propagation and also updating the weight, and that's what these two lines are about. So this will back propagate this loss, and the next line step will actually update the weights. And next, the all important step of weight clipping. So once my weights are updated, that is my critic weights are updated, now I have to clamp them or clip them, and I do that with these lines. That is, I run a loop for each of the critic.parameters values, and then I do p.data.clamp to and then pass these clip value, minus clip value and plus clip value. And what is my clip value? That's coming from the hyperparameters, and I kept the clip value at 0.005. So the way this clamp underscore method will work is that it will take two values, minimum and maximum, and if the values are less than the minimum, they will be replaced by the minimum value, and if the values are greater than the maximum, then they will be replaced with the max values. So up to this point was my discriminator or the critic training, that is up to here. It started from these using zero grad. So now I have to start the generator training, and as we discussed in the initial architecture, that we have to make sure that the generator trains after only so many times the discriminator is trained. So basically we are going to increase the training iterations of the critic so that it works to approximate the real distribution sooner. And that's why I am making use of this if condition, that is taking the modulus of hp.n underscore critic to be 0, and only then I will train the generator. And what is my n critic? Let's quickly see the hyperparameter definition at the very top. My n critic is 25. So only after 25 iterations of my critics training, then I will train generator. So generator will train after each 25 iterations of critic training is done. All right, now let's see what I'm doing in the generator training. So first, again the same line, I'm making a clean set of the gradient by making use of zero grad. And after zero grad, as per the original workflow of generator training, I first have to create some fake images with generator model and then apply critic on those fake images. So this line is first creating the fake images by bringing in generator object, and to that I'm passing image shape which has been defined earlier, and z is coming from that's a noise vector that also we have defined earlier. And then the generator loss will be just pass these fake images as input or argument to my critic function and take a negative of that. That's my generator loss. And then after the loss is calculated, I'm just implementing or just executing backward and step to do the back propagation and update the weights. That's it. And then pretty much my critic and generator training is done, and the next these few lines are just pretty obvious. I'm just calculating the total number of batches done till now, which will be equal to epoch, the current epoch multiplied by the length of the trained data loaders plus this iteration. So this I is a current index number. So that's my batches done, and why this is required, it is just to print some statement here in these lines here. I'm just printing the current state of the training. So that's this whole thing is my training method up to here. And then as a final line in my train.py file, I'm just executing this method, and that's it. Now everything is ready. Only thing is I have to run this or execute this train.py file. So let's go back to my Google Colab. Yeah, so this is a simple notebook that I'm using over here. It has got just pretty much just three cells. The first cells, I'm connecting my Google Drive, and because I definitely need to use GPU, so I'm changing the runtime to use my GPU change runtime type, and you can see I'm using the GPU here. And this NVIDIA SMI command will give me what kind of GPU I got. So here I got a Tesla K80 with 12 GB of RAM. That's good enough. And then the important thing is that to the these collab to the collab session storage, you have to upload these three files that we have our all codes in, that is train.py, utils.py, and wgan.py. So that's what I did here. I have uploaded these files. We can just double click it to see the files. Yeah, that's my files. And the way to upload it is just simple. You just content is your default directory. When you open up your Google Colab, just right click on it, upload, and select your drive. That's all you need. So that's how I uploaded these three files. So I have got all the three files, and now I only need, and you can check that by running this ls command. Yep, so I have train.py, utils, and wgan, and then the final cell, just python train.py, that is, you are executing the train.py file. And why I needed to connect my G drive is because in my train.py file, my root path has been defined to be my Google Drive, because that's where I have saved my MNIST data. Where is the root path? Yeah, here. So I have a root path defined here. That's where my fashion MNIST data were saved. So let's execute train.py. And it started running. Yep, the epoch started. Actually, here I am actually printing or showing the images, but when you run a train.py file like this in a Colab notebook, you will not be able to see the actual images. Rather, something like this will come, and this has already been recognized by, this is an open issue in their GitHub repository. To visualize actual images that this training is printed, that is when my images are gradually getting trained and they're resembling more and more like the original fashion MNIST. That will, to see that, you have to run the entire code in a notebook. And to the description section of this video, I will also give a link of this entire code, and you can just paste all the codes in a single notebook, and then thereby you will see the actual images. But here, just for showing you, let me run the actual notebook so that we can see the images. So anyway, we can see the epochs are running. It's actually running in a pretty reasonable time, each epoch just getting over in 1.5 minutes averagely. And here I am. I just included all the codes from the three files into a single Jupyter notebook and uploaded that notebook in Google Drive. Sorry, in Google Colab. And now I will be running this notebook and see what kind of result I'm getting. Yeah, let's just I have to restart this whole notebook, and then I will run it and to show you the images that is being produced through the training. And this is where I just started the training in Google Colab, the entire notebook. And so after each epoch, this kind of images will be produced. So I am still at my epoch 2, and that's why I'm getting these almost noise kind of output. But after you go past to like 50 or 60 epochs, you will see very much realistic looking fashion MNIST data set being generated from the entire network. And that pretty much wraps up this video, and I will put the link of the GitHub repository in the description of this video. Just search by the number. And also note that in this video my purpose was to implement a very simplified version of Wgan, and that's why I did not include gradient penalty in this one. So in the next video I will do another Wgan implementation where I will include a gradient penalty, and also instead of the fully connected linear layers in generator and discriminator I will use conv layer. So stay tuned. And finally, over the next couple of months, I will do many popular GAN or generative adversarial network implementation from scratch with PyTorch. So stay tuned and do subscribe. Thank you very much for watching. See you in the next one.